So we dealt with evaporation. Now, what makes clouds? So I argue that what's evaporating, obviously, what's evaporating is going to be making the clouds, right? Because it's a cycle. So what's evaporating are the water vesicles, which have net negative charge, and hydronium ions, which have positive charge, right? So you got negative charge and positive charge. And the argument, the central hypothesis is that a cloud will occur when these negatively charged vesicles, which have no tendency whatsoever to come together because they're all of like charge. But if you got positive charge from somewhere, which I'll discuss in a moment, the positive charge will bring them together by the like mechanism. That's Feynman's mechanism to form a cloud. So you have a situation that looks something like this with basically with distinct clouds. Now, so the first question is, well, what keeps the clouds suspended in the sky? And I'd like to suggest to you that it has to do with the charge of clouds. Now, we all know that at least some clouds have lots of charge, but it turns out that all clouds have charge. And this is evidence dating from the, I think, 1940s. And so when people were seriously interested in finding out what's going on up there, I think my understanding is now atmospheric science is mostly centered on computer modeling rather than on essential physics. Perhaps I'm wrong on that, but I heard that from someone inside the field. So one of the things that I don't know how many people are aware of, I was absolutely not aware of this. And I started my entire career as an electrical engineer. My undergraduate degree was electrical engineering, and nobody ever suggested to me that there was something called an electric field of the earth. No professor ever said that. We all knew that if you plugged a plug into a receptacle, that third prong, the round one, we thought it plugged into zero, into net neutrality. But when a Russian colleague came to my laboratory and started telling me about the Earth's electric field, I said, Andre, are you sure you're not on some kind of drug? I know about the Earth's magnetic field, but I never, ever heard of the Earth's electric field. He said, really? He said, every middle school student in Russia knows there must be something deficient about your American educational system. Well, yes, there may be. Indeed. He said, don't you know that the Earth is negatively charged? And up there are positive charges, either in the ionosphere or somewhere up there. And when you have positive and negative, you have an electric field between them, just like a capacitor. I said, Andre, I never heard of such a thing. You're nuts. I went home, scratching my head, losing even more hair. And I woke up in the morning, and then one of my students hands me the volume 2 of the famous 3-volume lecture set of the great Richard Feynman. Again, Richard Feynman. It's read by almost every graduate student in physics, at least in the US. It's got humor in it, et cetera, and wisdom. And he's talking about the Earth's electric field, which is about 100 volts per meter at the Earth's surface. And he's talking about the fact that the Earth is negatively charged. For me, that was a complete zinger. I could never imagine, because whoever could imagine the Earth was negatively charged. But in Feynman's chapter, he presents the evidence for it, not his own evidence, but evidence from many people before him. So I became convinced after looking at that evidence that indeed the Earth is negatively charged, net negative charge. And this is absolutely critical for everything we think of, and I will explain why. So the Earth's surface is 100 volts per meter. Before I go into it, just a little side issue. You've seen pictures like this before. Here's the Earth. Here's the atmosphere. It's actually it's not very high when you think about it compared to, say, the radius of curvature of the Earth. And the question has always confused me a bit, I must say, atmospheric pressure. What pulls the atmosphere out so that it clings to the Earth? And the usual interpretation is you have a stack of molecules and they're pressing on one another. And of course, it will press on the Earth. And the higher the stack, the more the pressure. That kind of makes sense, except it doesn't make sense because the atmosphere is full of air. And by definition, a gas is a state in which the molecules almost never interact. So it's not like a pile of bricks. It's a pile of molecules that rarely interact with one another. But there's another interpretation now, given the fact that the atmosphere is positive and the Earth is negative, plus clings to minus. The atmosphere clings to the Earth in a very simple way. And so the question is, does the atmospheric pressure, the clinging force, explain atmospheric pressure? Is that the reason why the atmosphere sticks to the Earth? And is that the reason why the atmosphere doesn't blow away? It's stuck to the Earth because it's positive and the Earth is negative. So this is an important issue that I'm raising. And when you go back to the clouds, which I argued has a structure something like this, with these little droplets held together, they're negatively charged, held together by the positive charges that tend to bring them together. Of course, they won't bring them together all the way, because once these negative charges come too close together, the repulsive force then keeps them from condensing even further. And so when the repulsive force balances the attractive force, it's stable and it remains stable. But what keeps these negatively charged clouds suspended in the sky? Well, it's a sort of no-brainer. If the Earth is negative and the cloud is negative, then repulsion, simple repulsion, should do it. But you might ask the question, okay, but charge forces, they're pretty puny. Are they really going to make the difference? Charge forces are by no means puny. And to give you an idea about how big they are, here's one example. You can find this in the internet or textbooks in many places. So this is an old-fashioned 120-watt bulb. And the idea is, and here's another one. Okay. And the idea is the current runs through this filament, and as it runs through, it gives off a glow, which gives you light and heat. And the idea is capture 1 second worth of the electrons in here. And if you could capture them, just 1 second's worth, and in a thought experiment, of course you can't do this, but in a thought experiment, condense them to a point, and then do the same for a second, condense them to a point. Okay, so here's the Earth, and you've got this charge cluster here and this charge cluster here. Each one only 1 second's worth of current through a filament. That's all. So the question I raise to you is how much weight? I mean, there's a tendency, this is negative, and this one can't go down because you got the ground here, but this one can certainly go up. And how much weight would you have to put on top of this one to prevent it from rising? Now, if I were to ask you the question, I've asked the question to various people, and the answers that you get vary all over the place, from 1 gram to 1 pound to maybe a kilogram or something like that. And you know what the real answer is? Okay, if you express the force in newtons or even pounds, it loses its impact. So I like to do it in terms of garbage trucks, because everybody has seen a garbage truck. It turns out that you'd need to put 50,000 garbage trucks on top of this cluster of charges in order to prevent the upward rise. In other words, the repulsive force is so large that to balance that repulsive force and keep this charge cluster where it is, you need 50,000 garbage trucks. Or if you prefer, something like 5,000 747s. That's how big the force is. If that example is not enough to give you a sense of charge forces, remember, this comes from 1 second's worth of electrons flowing through a filament of a light bulb. That's it. Well, here's another example, and this one comes from Feynman himself, sense of humor. So here you've got 2 individuals, man and a woman, and suppose this guy, this is you, lying on the ground, and suppose you're able to remove 1% of the electrons in your body. Okay, that leaves you with net positive charge, right? And then your companion up here, you remove 1% of her electrons, right? So both of you now are positively charged. You might like otherwise, but you'll be repelled. The 2 of you will be repelled, right? Because she's positive, you're positive, and she's going to rise up. Same as the previous, but this is a little bit of a different example. Okay, so my question to you is, how much weight would you need to put on top of her, pressing down on her to prevent her upward rise? Can you take a guess?
No idea. No.
Oh, okay. Well, again, I've asked to many people, and I get answers like a kilogram, a pound, and such. And the answer comes from Feynman himself, who did the calculation. I didn't do the calculation. He did the calculation. And the answer, the weight that you have to put on is equal to the weight of the entire Earth.
Right.
Prevent her from moving upward. Force that's so staggering that it's unimaginable. So bottom line from these two is charge forces are absolutely huge, much larger than most of us think. What keeps the clouds suspended? Well, we've got the Earth, which is negatively charged, and we've got the clouds, which are negatively charged. And so, if you have a cloud that has not too much negative charge, it will sit up like this. If you had a cloud that consists of a lot of negative charges with few positive balancing charges, you see, then the repulsive force is greater and it's going to rise higher up. And therefore, you could understand why you can have clouds sitting on top of one another at different levels. It's all repulsion. This is repelled by the Earth, this is repelled, and this is repelled more because it's got more charge. And repulsive forces are very large. This one's got more negative charge, less negative charge. And so you can understand why, for example, you can have stacks of clouds sitting on top of one another. Usually they have a different form because they arose in different regions. They have different water content, different charge contents. And why can they stack in this way? And I think the reason they can stack is this one has high negative charge and it repels the Earth profoundly. This one has medium negative charge. And this one has low negative charge, lower. All negative charge, but different amounts and therefore different heights. So I told you about condensation of clouds and how clouds form, I believe, from the like principle. What about precipitation? We get a lot of that here. What causes rain? We read about or hear about pressure, low pressure, hear about temperature, and we hear the people on the TV and the newspaper wax enthusiastically or unenthusiastically about low pressure and high temperature and a lot of jargon, which frankly for me is not so simple to understand, but almost nobody talks about electrical charge. In fact, I must say that in the past 5 or 10 years, since I've begun thinking about it, I don't think once I've heard the word electrical charge in the context of weather. Yet, what I've been telling you and what I'm continuing to tell you is that electrical charge is absolutely central to all of weather. And of course, everybody has seen this, so we know that under extreme conditions, this is the case. But I want to talk to you about induction. And anybody who studied even Physics 101 will have learned something about induction. This is one of the principles that's really simple, easy to understand, and probably even true as a result. It comes from Michael Faraday, the famous Scottish electrophysicist. So if you have a charge sitting up here, and this is the Earth with a house, if the charge is low enough, if the charge is really high, it has no impact at all. If the charge is low enough, what happens is it induces equal and opposite charge on the surface below. That's the principle of Faraday induction. The closer it gets, the more powerful it gets. And the same thing occurs if it's negative charge. It'll induce a positive charge beneath. And the closer it gets, the more positivity. It's always attractive once it starts happening, always attractive. And that's really important. And you can see an example of it by taking a balloon, rubbing it on your shirt to charge it, and putting it next to some water, and the water will always bend toward the balloon. And the reason, it's really dramatic to see if you haven't tried it. Kids love it. The reason, I believe, is that you've induced charge on the surface of the balloon by rubbing it on your shirt or a towel or whatever, and it will induce opposite charge on the stream of water, and the two will attract. And so the stream, instead of going straight down, it will bend toward the balloon beautifully. So induction is very important. Now, let's go back to the vesicles and the positive charge. Remember, I suggested to you that when you have humidity that's rising, usually in warm areas, lots of it, and you have positive charge, which also comes from evaporation, but not necessarily in the same position. When the two have gotten together, you've find a cloud that looks like that. And remember, it's not necessary to have a whole lot of these positive charges for the glue to hold it all together. So the cloud has net negative charge. And so when there's enough positive charge in the cloud, remember it's net negative, when there's enough positive to lower the cloud sufficiently, then the induction effect begins to take hold. And as soon as the induction effect takes to take hold, the whole cloud then begins to be attracted downward. And as the rain occurs, when the cloud comes down, you first, if you have mountains in the background, you begin to see the tops of the mountains obscured, gets lower and lower until finally you've got rain. You need the lowering of the clouds to get it. And I believe that precipitation therefore occurs inductively, that you've got the positive charges here are pulling on the lower surface of the cloud, pulling on these negative charges and pulling them down individually as rain droplets coming down. And so the principle is that the rain droplets don't just drop, they're pulled down. And what's the evidence for this? A paper about 10 years ago actually measured the velocity of rain droplets falling. And you can calculate if it's free fall, if they're just coming out of the cloud and dropping, based on their size, you can calculate what the terminal velocity would be. It's like if you jump out of a tall building, but you won't continue to accelerate, you reach a terminal velocity. And you can calculate that based on the physical properties of you or the droplet or whatever is falling. They did that and they reported velocities up to 10 times that calculated from free fall, meaning what they concluded and what is sensible is that the droplets are actually pulled down. Rain droplets are pulled down. They don't just drop. They don't just fall. They're pulled down to the earth. And that's why you can sometimes get pounding rain. Now, what about wind? Where does wind come from? How do we explain? Is it pressure gradients? Well, pressure gradients amount to a convenient way to think about where everything comes from, but it's hard to explain. How do you get a gust of wind from a pressure gradient? Why doesn't the pressure gradient just even out quickly? Why does it sustained enough to give you wind, either sustained winds or gusts of winds? How do you do that? But there's another possibility, and that is charge gradients. So if you think now about the Earth with its negative charge and up above in the atmosphere where you've got those hydronium ions sitting up there, if you think about this is not a cloudy situation with protons diminishing with increasing altitude, think about what happens in day versus night. So it's the sunshine hitting the earth that drives the evaporation, right? You need energy. I said infrared energy, and infrared energy comes from the sun. But at nighttime, you don't have that energy coming. And so these positive charges ought to be dropping down, and they do. This has been demonstrated. So in this case, with all these positive charges here and negative here, you have a high electric field, and here you have a low electric field. And indeed, that is actually confirmed. So you have electric field here versus time. And if you forget the entire world, because it's a composite of all of these, just look at one of them. For example, look at the Americas. So you have darkness, you have a low electric field, and then roughly these hours, which correspond, this is GMT, late afternoon when the sun has had a chance to exert its effect, you get the highest electric field. And it occurs different times at different regions around the world, depending on when they are getting their sunshine. So the sunshine, the presence of sunshine is creating this evaporation, which creates the electric field. And so it'll vary with time of day. So, who turned off the lights. But there's a gradient, see a sharp gradient between light and dark. And so, for example, here's New York and here's Seattle. And in the case of morning sunshine, you have a situation that looked like the sun has already reached New York, and then Seattle is still dark. And all these positive charges have begun to rise up, but not here, but here. And so you have positive charges here, few positive charges here, a gradient of positive charges, and then a wind, effectively a wind, because these positive charges, they want to escape one another. They want to go to where there are no positive charges. And so they're blown in this direction, and you get wind. And you can imagine a wind gust occurring, because if you have some region of the earth where something on the earth is prone to releasing positive charges and the next region is not, it could be natural, it could be industrial. You can imagine that you get a gust of wind from a local charge gradient. So I think this is a more logical explanation for the origin of wind.